Okay, so well, let us get back to our class. Last week we well we discussed about VLE, right? The vapor liquid equilibrium, and we start from VLE at low pressure because this is the most simplest one. And well, we learned about using K factor, right? The K value where K is a Y over X, right? Ki is a Yi over Xi. And we learned about relative volatility. And what else? Then Raoult's law and modified Raoult's law, right? Where we use what is it? The fundamental from thermodynamics. Mhm. And we set the Fugacity of component I at different phase, at vapor phase and liquid phase must be equal. And then we derive YIP equal gamma I XIPI, right? This one is correct when the pressure is low, right? Only at low pressure, yes, because at low pressure you can assume that the Fugacity coefficient becomes 1. And yeah, Fugacity then can be replaced by pressure. Okay. And we learned about ideal solution, type 1 solution, where gamma activity coefficient for both components. No, yeah, right. For both component must be 1, right? And the next one is type 2. Type 2 is positive deviation, where we have a repulsive interaction between molecules. So molecule try to be away, and what is it? It yields gamma for both phase must be higher than 1. Okay. So when you take log of gamma is positive. Okay. And the next one is negative deviation. In case of negative deviation, so we have a opposite interaction with type 2. So the gamma in this case must be less than 1. Okay, when you take log, of course, it's negative. Mhm. And for both case, we have azeotrope. For type 2 and type 3, we have azeotrope. In type 2, we have minimum boiling point azeotrope. And for type 3, we have maximum boiling points azeotrope. Okay. And then type 4, for type 4, it's a heteroazeotrope, where we have a VLLE. We have two phases of liquid. Okay. And also the azeotrope occur at two phases of liquid. Okay. And in case where we have a non-condensable component, then we can use Henry laws instead. Like you have water and oxygen, water and nitrogen, something like that. For nitrogen and oxygen cannot be condensed at normal pressure. Then we discuss about the calculation related to VLE. We have bubble point calculation, and we have two types of bubble point calculation. One is, when temperature is given, and the second one, the pressure is given. Okay. Okay. The pressure is given. And we also have dew point calculation, where dew point calculation, you start from vapor phase, okay? And then you're given with temperature, or you're given with pressure, okay? Okay. Also, we have traditional K-factor method, which is is empirical, okay? You need the chart, okay? And you have to draw a line between specified pressure and specified temperature, and you read the K Okay, from each component. Okay, we have what else? We have boiling point elevation. We have freezing point depression. Okay, so well, now we move to the next. Just one moment. Next chapter. The next chapter is we are dealing with. Just one moment. How can I control this? Should be okay now. No. Okay. So, maybe one moment. I will give you the slide and also file for the next chapter. Okay. Previously, I gave you chapter 8 or chapter 7? Chapter 8, right? So now we move to chapter 9. So where is my line? Okay. And what else? Slide, we still use the same slide. And okay, this one. One more slide. And this one should be PDF, right? If I give a keynote, you cannot open it except you use MacBook or iPad. Okay, one moment. Got the file ready. So, okay. Yeah, you got both file, right? One is textbook, okay? And the other one is slide we're going to use today. Okay, so back to, where is it? Here? No. Okay, so now you see that from our VLE model, where is it? Okay, here. This one? No, this is chapter 8. The previous one. But I will, well, I'm going to tell you why we need chapter 9. Okay. You see, on the left-hand side, we deal with fugacity of vapor, right? And fugacity vapor, of course, we assume low pressure. So fugacity coefficient becomes 1, right? Right? Where is it? Okay, here. Okay. Fugacity coefficient becomes 1, right? So, well, on the right-hand side, we need activity coefficient. Okay. And of course, for activity coefficient, you need the model. All right. Okay. Activity coefficient model. And if I give you this table, the experimental data, can you calculate the gamma at each equilibrium? Each point is, each row is one equilibrium, right? This is one equilibrium. This is also one equilibrium. This is also one equilibrium. Can you calculate it? I mean, calculate the gamma from this table? Yes or no? Yes. How can you calculate it? Hmm? How? You have x1, you have y1, right? And you know P, right? P, pressure of the whole system is kept constant at 1 atm. and you know T, temperature. So by using Armstrong equation, you can calculate PI because it's related to T. Okay, you know Y, you know X, you know P, then you can calculate gamma. Okay, you know everything, right? And for that, it's for the first component, X1, Y1. What about X2 and Y2? Yeah, different gamma, but how can you calculate it? You can calculate it? Yes or no? Yes, because this is X1, you can calculate X2 by 1 minus X1. And for Y2, you calculate it by 1 minus Y1, right? Okay. And for P, no. Okay, P here. We know temperature, right? The same temperature, but different Armstrong equation. This one you need the second component. Okay, component 2. Okay, and P we have the same P. Okay, so you see that from this table you can calculate everything. I mean gamma 1 and gamma 2, right? Okay, and the question is that gamma is correct only at each point. Okay, if you want to calculate at other place, I mean something between this point and this point, you don't know because you don't have information about gamma, right? That is the reason why you need model. Okay, and of course if you need model, well, you need, if you want to calculate at the point, of course you need different gamma at different point. Okay, then you need a gamma model. Okay, model for gamma. And the question is, how can we construct, how can we create such a model? Okay, in chapter 8 we assume that we know that model, and we, which one we use? Van Laer equation, maybe? Yes, we use Van Laer equation, right? Van Laer equation. Here it's a model of gamma. Okay, but anyway, how can we do our own? How can we create our own model? Okay, of course, even you want to use gamma Van Laer equation, but still, if, well, someone already studied that, you have a b, okay, parameter for Van Laer equation for that pair of mixture. However, if you, well, you want to know a new mixture, a mixture contain new component, you have to do it by yourself because no one do it before. No one well prepare such information before. So that is the reason why we need chapter 9. Okay. So one thing before we directly discuss about the model of the activity coefficient, let me, well, emphasize that you once you obtain the data, you need this Gibbs-Duhem equation. You have to consider Gibbs-Duhem equation first. Why? Remember the Gibbs-Duhem equation? Do you remember Gibbs-Duhem equation? This equation? Gibbs-Duhem equation? No? Yes or no? Yeah, just I think, well, before midterm you learn it. Yeah, the same people who invented that Gibbs-Duhem. It's developed by Gibbs and Duhem. Yeah. Okay, all right, no problem. I try to cut everything short because I cannot cover that part. Okay, it takes too much time. In, well, in the first class, we review the EOS already, but okay, for any property, thermodynamics property, okay, it must follow the Gibbs-Duhem equation. Okay, so you take derivative of one thermodynamic property, okay, in respect to XA, let's say, okay, and then plus XB over XA, and you take derivative of that thermodynamics property, okay, respect to XA, it must be equal 0. Okay. Well, from here maybe it's quite, yeah, how can I say, because it's derivatives already. Okay, but if you can connect the how we can derive this one, but actually it's not that difficult in order to derive it. Okay, but in order to keep everything short, the property, any property, yeah, it can be, it gives or gives energy or other thing, it must follow Gibbs-Duhem equation. Okay, after the class you check Gibbs-Duhem equation again, and then you will see. Okay, and log gamma also the thermodynamics property. Okay, so it must follow the Gibbs-Duhem equation also. Okay, so you see that experimental data, all the experimental data must follow Gibbs-Duhem equation, because Gibbs-Duhem equation is the mathematic property. Okay, it might be always true. If you perform experiment and you apparently the data you obtain do not follow the Gibbs-Duhem equation, then what does it mean? It's your data contains error and you have to correct it. Okay, so I will tell you later about the method to check, to validate, to check the validity of VLE data. Okay, yeah, today we will learn about that. But first, remember that the gamma A and gamma B are not independent. They are, must be in agreement with the Gibbs-Duhem equation. Okay, so that means if you invent new configuration of gamma model, it must follow the Gibbs-Duhem equation also. Okay, you cannot just arbitrarily write the activity coefficient model. Okay, because the configuration must follow the Gibbs-Duhem equation. For example, this one, if we write log gamma A as linear equation like this, very simple. Log gamma is A xa plus B. Log gamma B is C xb plus D, like this. Do you think it's usable? Yes, you think it's usable, this type? Yeah. Why? Why you think that it's usable? What I emphasized later, previously, that log gamma A and log gamma B are not independent. Okay, so if you think it's usable, it must be in agreement with this Gibbs-Duhem equation. Okay, so let us check. You have log gamma, right? Log gamma A, and then you take derivative, depends on XA. Okay, and log gamma B, take derivative respect to XA also. Okay, no worry, XB is 1 minus XA. Okay, and you see that once we do that, we obtain this equation. Okay, we plug this type of equation in, give to him equation, and you see that we obtain a minus xb over xa times c. So what does it mean? Give to him equation, this term must be 0, right? Must be 0 here. Okay, and in order to make it to be 0, you see that xb over xa must equal a over c. Then you see that we cannot have different fraction xb, well, of xb xa. It's only valid when xb over xa equal a over c. All right. So that means these expressions cannot be used because it's not cover other fraction. It cover only when xb over xa equal a over c. Okay. But in reality, of course, we need xa vary from close to 0 to close to 1. Okay. That means xb over xa vary from, well, infinity to 0, right? So it's impossible that, well, we use this type of equation and we can model every point. Okay. So in conclusion, this model, the linear model of log gamma A, log gamma B, cannot be used because it does not follow the Gibbs-Duhem equation. Okay, you get my point? People assume you, if you have question, you can raise your hand and you can turn on your microphone and ask me anytime. Okay. Okay, good. So you see from the data, from the very first table, I asked you to think about the calculation of gamma A, gamma B, right? And I told you that, well, we don't have gamma in between the state. That means you cannot just, what is it, interpolate between point for gamma because linear function cannot be used here. Okay. It's okay. We go back and forth.มันเป็นอะไรก็ได้ที่อยู่ระหว่าง0ถึง infinity ถูกไหมล่ะเพราะว่า component เราต้องการเวลาเราไม่รู้อยู่แล้วถูกไหมไอเนี้ยถ้าใช้โมเดลเนี้ยมันจะใช้ได้แค่สัดส่วนนี้เท่านั้นใช่ไม่ใช่ความหมายไม่ใช่อย่างนั้นความหมายคือ configuration เนี้ยรูปแบบโมเดลเนี้ยมันใช้ไม่ได้เพราะว่ามันไม่สอดคล้องกับ Gibbs-Duhem equation ต้องไปใช้โมเดลรูปอื่นมีเยอะแยะแหละที่ใช้ได้มันเป็นลีเนียร์ไม่ได้คือเราไม่สามารถเดาเป็นลีเนียร์แล้วก็นั่นได้เลยอะไรเงี้ยเพราะว่ารูปแบบของโมเดลจะต้องสอดคล้องกับ Gibbs-Duhem equation โอเคไม่จำเป็นขึ้นกับ Gibbs-Duhem equation ครับตราบใดที่ Gibbs-Duhem equation ถูกมันก็ไม่ผิดโอเคใช่ไม่เดี๋ยวกำลังจะพูดไงว่าแล้วแบบไหนโอเค so you see linear equation cannot be used for the model of activity coefficient model, right? So so once you obtain the data from that table, you cannot just, wow, look like linear and then you approximate to be linear, right? Because it cannot meet our demand. So which configuration of the activity coefficient model can be used then? Linear cannot be used, right? The simplest one is Walla equation. This equation, you see. You can try on this equation for Gibbs-Duhem equation. And you see that this one perfectly follow the Gibbs-Duhem equation. Now you have to find the derivative, of course. Yeah. And replace xb by 1 minus xa plus. Okay. Okay. You can do it later and you see that it's follow Gibbs-Duhem equation. Okay, so the next thing is now we know the configuration of the model. Okay, the structure of the model. Okay. The next question is, okay, now we know that possible structure of the activity coefficient model. The second question is, how can we model it? How can we find the parameter? Okay, because even, yeah, this Walla equation is correct. If we follow this, how can we find A and B? Okay, so we have to look at the excess Gibbs energy. For excess Gibbs energy, yeah, you learn it before midterm. If you still remember. If you cannot remember, just go back and read a bit. Excess Gibbs energy, ไม่ได้เรียน before midterm. Oh, if you don't learn excess Gibbs energy, Gibbs-Duhem equation also. Yeah, neither. Oh, then it's okay. You read it by yourself. Yeah. Excess Gibbs energy and Gibbs-Duhem equation. Okay. But anyway, if we focus on excess Gibbs energy, we know excess Gibbs energy. Oh, what is excess Gibbs energy? Excess property. What is the idea of the excess Gibbs energy? When we say excess property, we model it by take the difference from the real property and the property when we assume the mixture as an ideal solution. Okay. So excess property, it's the property which is deviate from ideal solution. Okay. So if we look at the Gibbs energy, excess Gibbs energy, it's of course it's actual G subtract by ideal G. Okay, G is Gibbs energy, of course, and this excess Gibbs energy can be calculated by summation of Ni RT log gamma I. Okay, if you want to know how can we derive this, yes, I can give you the chapter related to this, but you have to study by yourself. Okay, so if we what's it? Yeah, this is RT log gamma I, right? Get excess Gibbs energy, and if we work with fraction instead, we divide it by the total mole, then we can write, yeah, in this form, summation of xi instead of ni. Xi is a mole fraction, right? Xi RT log gamma I. Okay, and for binary, for binary mixture, we know at each equilibrium R is constant and temperature also constant, so you arrange the RT again, you divide RT by both sides. So on the left hand side we have GE over RT. Okay, And the right hand side, because we consider only binary, okay, it's a binary mixture. So it becomes x1 log gamma 1 plus x2 log gamma 2. Okay, you can say A and B is the same. Okay, so the good news is if you plot between GE over RT, okay, from the VLE data, yeah, remember the table at the beginning of the slide, you can calculate gamma, right? Gamma 1, gamma 2, right? And you take log and wow, multiply by x1 and multiply by x2 here, and then you take summation of it, and then you plot GE over RT, because you can calculate GE over RT, right? You plot GE over RT from 0 to 1. Okay, you will see that GE over RT look like this. Okay, of course, for different components, it show different thing, but you see that it's not, it's kind of quadratic, or well, it's deviate. It's not linear for sure. Okay, look like this. Okay, and the good news is if we divide GE over RT by XA XB again, okay, the shape of the this curve change, and it looks more like linear function. This line, I cannot say line, but yeah, but you can approximate as a linear, right? As a line. Okay, this one is GE over RT. This one is GE over RT XAXB. Okay, so we can approximate this one as linear. And when it says linear, you have two choices. The first choice is you see that it's linear and the slope is more or less close to 0. And if I approximate the slope, it's 0. It is a line, right? A linear function with slope 0. You have only one parameter, which is the intercept of y-axis. Okay, so that means you take average of each. Hmm? Okay. 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 If you don't want to use one parameter, you need two parameters. Then you can model GE over RTXA as AXA plus B. And in this case, you have two parameters. Okay. So what happened if you have only one parameter? If you have only one parameter, you get this model. Log gamma A equal AXB squared, and log gamma B equal AXA squared. Okay, where A is the parameter you obtain. Okay, the average of each point. Okay, good. We call it the symmetrical equation. Okay, or symmetrical model. Okay, and do you think that this model, symmetrical model, is in agreement with Gibbs-Duhem equation? You can try. You take log derivative. Okay, A is constant, right? So we have 1 minus XA square, right? So you obtain 2, 1 minus, yeah, you can derive it. 2 minus, no, 2 times. Hmm? No. XB is a function of XA. 1 minus XA. Okay. Okay. And you get minus 2XA from this. And for this term, you get 2AXA. And then you take summation of it, becomes 0.นี่คือคิดอยู่ครับOkay, so and if you take two parameters A and B, AXA plus B, you can from this model from this data you can find what's it, linear regression, and then you get two parameters, right? Slope and intercept. And then you will get this model instead, the Marcuse equation. Log gamma A and log gamma B. Okay, you see, log gamma A is XB squared times B plus 2 C minus B XA. Okay, and log gamma B is XA squared times C plus 2 B minus C XB. Okay, and what is B and C? B and C, well, because we obtain from the data, from the fitting the data, we obtain A and B, right? And here how C and B derive. Okay, A plus B is C. This C is A plus B. Okay, and this B is this B. Okay. Okay, now you can derive your own parameters. So what is the difference between Marcuse and symmetrical model? You see that we can, if we use only one parameter, of course, finally we obtain symmetrical model. And symmetrical model, when we plot the the calculated gamma from experimental data and from the model, okay, you see the difference. Mm-hmm. What do you think about Marcus and symmetrical? Of course, both capture the whole, what is it, behavior of gamma A and gamma B. But the main difference is, you see, for symmetrical model, the error, okay, the deviation, well, the error distribute over the whole range, right? You see, the symmetrical model. Mhm. Even at the beginning, of course, it's still deviate from the experimental data, okay? But for what about symmetrical? No, yeah, between symmetrical and Marcus. You see that for symmetrical, sorry, yeah, I think I explained wrongly. For symmetrical, you see that at the center, the error or deviation is lower, is smaller than this area and this area, right? Consider the dashed line and experimental data. You see that at on the leftmost and on the rightmost, the deviation is much larger than at the center. Okay. However, in Marcus, well, it's distribute the error over the whole range. The error here and the error here, well, not that much difference. Okay. Marcus. Mhm. อยู่ตรงกลางไม่เกี่ยวอะไรกับไอเดียไม่เกี่ยวอะไรกับไอเดียที่เกี่ยวก็คือ yeah, when we, because the parameter we take from average, right? And you see that if you write, you draw a line, a horizontal line at the center, the error is much lower, smaller than on the rightmost and leftmost. Okay, so that's why the result, I mean log gamma, when you plot log gamma here also on the rightmost and leftmost, well, contains much deviation. Okay, but in case of Marcus, because you you use two parameters, okay, and you draw a line with slope, okay, so you already average distribute the error, okay, between all area. Okay, so the difference, the main difference is symmetrical use only one parameter and Marcus use two parameters, okay. And if you look at the chapter I sent you, you can find this table. Okay, from this table, you see, for symmetrical model, okay, use only one parameter, okay, and the result model is log gamma A is AXB square, log gamma B is AXA square, okay. What about Marcus? Marcus take two parameters and you, well, model the GE over RTXAXB as this function, and you obtain log gamma A, log gamma B as this function, okay? And what about one line equation? For one line equation, once you plot GE over RTXAXB, you model this value, GE over RTXA-XB as AB over BXB plus AXA. Okay, you model this way, you find A and B, and then you obtain finally from A and B you obtain the activity coefficient model as shown here. Okay. And for Wilson in RTL, of course, it takes more parameter. Okay. Okay. Now we move to the next topic. Activity coefficient at infinite dilution. Well, for activity coefficient model, you need several experimental setup, and then you need a bunch of data. Okay, but you see that if we consider only some condition, we call that condition as the infinite dilution. The condition for infinite dilution is if you have pure A and you put one drop of B in pure A. Okay, what will happen? You is, well, if you measure that condition, the VLE at that condition, we measure the interaction between A and B. When B surrounded by A only, okay, without the interaction between B and B, okay. You imagine that we have pure A in the system, only molecule A, and you introduce one drop of B. Okay, so we can assume that one molecule of B is surrounded by all A. Okay, and no interaction between B and B. Okay, we can observe only interaction of B and A. Okay, so we call that condition as infinite dilution. Okay. Okay, so when we say gamma A infinity, that means XA is 0 and XB close to 1. Okay, becomes 1. Okay, POB, we introduce A, then XA is close to 0, right? And XB close to 1. Okay. And if we consider the Marcus equation, what happened? This Marcus equation, B is 1, right? XB is 1, XA is 0. This term becomes 0, right? This 1, so log gamma A become B, right? Log gamma A infinity becomes B. And you see that if we know the gamma at this condition, I mean gamma B, we can determine, we know the parameter B by using only one experiment. Okay? Log gamma A infinity is B. And well, at the opposite side, if we consider log gamma B infinity, that means XB becomes 0 and XA close to 1, right? In that case, log gamma B infinity is close, it's 0, it's C. Okay, so you obtain another parameter. Okay, for Marcus, we have two parameters, right? That means you need two experiments in order to obtain both parameters. Okay, this is another way to calculate the activity coefficient model. Okay, the parameter for activity coefficient model. Okay, what about one line equation? Okay, just check this. For one line equation, if we consider the case of xb close to 1, when xb is 1, xa is 0, what happened to log gamma a infinity? Log gamma a infinity is xb is 1, right? Xa is 0. This term becomes 0, right? We have 1 and 1 here. It's a. And log gamma b infinity, we have xa close to 1. This 1 close to 0. Yes, it's b. You see, even one line equation, you can find a parameter by using log gamma a infinity and log gamma b infinity. Okay, infinite dilution coefficient. Okay, just break for 5 minutes. ให้ลงแอดมันไหมอืมแม่จะไปอยู่ใครใช่ป่ะอ๋ออยู่กับอาจารย์อะไรเนี่ย Okay, shall we continue? So the next one is now we know how to determine the parameter for activity coefficient model, right? And also, well, you have two choice. The first choice is you have, well, multiple experiment, right? The number of experiment, and then, well, from that one, you plot between GE over RT XAXB, okay? And then from that one, GE over RT XAXB, from this one, you fit this curve, this GE over RT XAXB, right? Okay. Of course, you can use one parameter and you obtain symmetrical model. You can use two parameter CB and you obtain Marcus equation or Van Lam, whatever it is. Okay, so the next, okay, and then the other way is use activity coefficient at infinite dilution. Okay, 2 points you also obtain the parameter. Okay. The next one is the next question is we assume constant pressure. We determine the activity coefficient at certain pressure and temperature. Okay. The question is, can we use the parameter we obtain at certain pressure and predict the behavior of the system at different pressure? Okay. Now we look at, we have to consider this equation because this relates the activity coefficient model with pressure and also activity coefficient with temperature. Okay, so the derivative of gamma respect to P equal V bar minus V0, okay, over RT. So why this thing? On the left hand side, of course, is well, it tells us the how log gamma I change when P change, right? At constant T and Xi, of course. And on the right hand side, you see that how the activity change respect to P depends on the deviation or the volume change. Okay, what is this volume change? Is the change of the volume of, I mean, molecular volume. Okay, the volume of the molecule. Okay, when the molecule is in the mixture and when the molecule is in pure component, as pure component. Okay, the same molecule. Okay, the I component. But we take the deviation from when the molecule, that molecule is in mixture and in pure component. Okay, and what about this expression? This expression tells us how activity coefficient change with temperature. Okay, and it depends on the entropy and the enthalpy change. Okay, the enthalpy of pure component and enthalpy of mixture. Okay, that component in mixture. Okay, over RT square. Okay, and so you see, if if you want to estimate the change of the activity coefficient when the pressure change, we must know this value, this function. Okay. If we know the volume change when we dissolve, we mix A and B together, we can estimate it. Okay. And we can approximate that, we can treat that the gamma doesn't change when P change if the volume change is 0. Okay. When we get the 0 change, the 0 volume change, when will we get, at what condition? When the mixture is ideal solution. Remember ideal solution, right? For ideal solution, you mix A and B. The interaction between A and B is similar to A and A. Okay. So in that case, volume will not change at all. Okay. However, if you mix A and B and the volume, molecular volume of each component change a lot, you cannot approximate 0 change of activity coefficient when pressure change. Okay. So it's straightforward on that. You can look at what is it when you mix ethanol and water. Okay, one maybe 100 milliliter of ethanol and 100 milliliter of water. If you mix it and the volume is 200 milliliter, sorry. Yes, it should be no volume change, right? But in reality, it's the volume change occur, but a little bit. It's not perfectly 200 milliliter, right? But if that volume change is large, then the effect of pressure becomes very large. Okay. Yeah. For example, toluene and benzene, because toluene and benzene, it's type 1 solution, it's close to ideal solution, then you can approximate that. Wow, it's no volume change at all. And the second one is how the activity coefficient change when temperature change. It depends on heat of mixing. Oh, just one moment. Someone called me. สวัสดีครับ Okay, so what we call this term? Enthalpy change. When I said enthalpy change, but you are not, I'm quite sure that you're not familiar with enthalpy change. Enthalpy change because of mixing, we call it heat of mixing, right? So if in what case we have 0 heat of mixing? You know, heat of mixing, right? When you mix A and B and temperature doesn't change. No. Even no reaction, you still have heat of mixing. When you mix A and B together and the temperature doesn't change, that is no heat of mixing, right? But if you mix A and B and temperature drop or temperature increase, must be, there is heat of mixing. Okay? And what case we can observe no heat of mixing ถ้าสารเดียวกันเขาไม่เรียกว่า mixture ideal solution only ideal solution right the one condition of ideal solution is well no heat of mixing no volume change okay the same because the interaction between A and B is similar to A and A okay and B and B right so in that case no heat of mixing no volume change okay so you see you can if you know the heat of mixing as a function of T of course you can integrate it okay no problem you can estimate how activity coefficient change when temperature change okay integrate this function okay yes this is effect of pressure and temperature okay so you integrate this one if you know this value okay so the delta of log gamma we can approximate by okay this term when we approximate this one is constant and then you times it with delta p okay but if this value becomes zero of course no meaning the delta log gamma becomes zero okay right if there were no volume change on mixing then the effect of pressure change on activity coefficients would be zero okay and the same this one we can approximate this term okay this delta of the log gamma okay by integrate this term you move delta t on the right hand side and then integrate it okay log gamma a at t2 and over log gamma gamma a at t1 okay approximate by this average yes time with 1 over t1 minus 1 over t2 okay so the next slide is related to what is it liquid phase activity coefficient for ternary mixture what we learned so far is for binary mixture, but you can use parameter from binary mixture to estimate the ternary mixture. Okay, from this one. And the next one is Weber phase non-ideality. For Weber phase non-ideality, it's on the left-hand side, okay, where we at low pressure, of course, no ideality, non-ideality in Weber phase. Okay, on the left hand side is activity coefficient. No, not activity, Fugacity coefficient, right? Time with y and p, right? And we assume low pressure, so Fugacity coefficient becomes zero, become one, okay? But if the pressure is not that low, of course you deviate from what's it activity coefficient no Fugacity coefficient 1 to something else, right? You have to integrate, you have to find the phi I hat by yourself using EOS or whatever. Okay, for example this one we can use EOS, we calculate this way because phi I hat is exponential of minus 1 over RT integrate P0 to P, right? Alpha I dP. So you replace this with Z, okay, compressibility factor, and then you can use EOS, okay, to calculate it. Yes, that is how we accommodate the non-ideality in Weber phase. Okay. Okay, so well, okay. So we move back to the experimental data. Okay, at the beginning of this class, today class, we talk about when we perform experiment, VLE experiment, and we obtain data, right? Of course, we can do everything. Yeah, we can do so many things, not everything. Yeah, and of course, by using that data, we can find the what is it? We can construct activity coefficient model, right? But the first question we have to answer is, can we trust the data we obtain? Because if the data contains so many errors, okay, finally we will obtain very bad parameter, okay, the parameter which cannot reflect the real behavior, okay. So that question is, we call it thermodynamics consistency. If the data agree with or consistent with Gibbs-Duhem equation, we call it thermodynamic consistency, okay. If not, of course, if it cannot pass the thermodynamic consistency test, then you can discard those data, okay. Okay, so I told you that well, we will not cover that Gibbs-Duhem equation, but in this slide we cover that some part of it. You see that we can of course we can write summation of xi d log gamma I as ve over rt dp minus he over rt square dt. Okay, you can check the well how we derive this equation, but yeah, and at constant p and t, of course, finally this equation becomes this one, summation of xi d log gamma I, right? And we use this one, right? G over rt equal summation of xi d log gamma I. Yeah. Very often we use this. Okay, so now we assume that we know the Gibbs-Duhem equation, right? And we can write the Gibbs-Duhem equation. The Gibbs-Duhem equation can be written as this: x1 plus no, x1 d log gamma 1 plus x2 d log gamma 2 equal 0. Okay, this is very general form of Gibbs-Duhem equation. Beside the one you learn in the what's it? Okay, in the chapter we talk about. Okay, so from this expression we can use to determine the quality of the data, the VLE data. Okay, if both sets of data, gamma 1, gamma 2, we calculate from the experimental data, fulfill the Gibbs-Duhem equation. We say that the data satisfy the rules established by thermodynamics, or we call it thermodynamics consistency. Okay. So if you check the paper, all the paper report the phase equilibrium data. At the very beginning, the author must check the thermodynamic consistency. Okay. If the author fail the thermodynamic consistency, okay, that paper is useless. Okay. Even they report sophisticated system and report the what's it, the new data or new binary system, but it's useless because the experimental data cannot satisfy the Gibbs-Duhem equation or thermodynamic consistency. Okay, so from this one, okay, so previously you're familiar with this one, right? Yeah, this one. Take derivative depends on dx1. So if in a plot the variation of the activity coefficient, this is a what's it, variation of activity coefficient, right, with x1, okay, with consumption composition. We can draw a tangent. This is a tangent, right? The derivative is tangent. If we plot between this value, this log gamma 1 and log gamma 2 with x1, and we take the derivative, it represents the tangent, right? Tangent of the curve at any concentration, okay? And then we can measure the corresponding slope, right, from that one. So what we can observe. So the Gibbs, because the Gibbs-Duhem equation, we can integrate from 0 to 1, right? So with that one, we integrate from log gamma infinity, the infinite dilution to 0. Okay. Why we don't take from 1? Yeah, it is the same condition, but 1 is we accept the 1 because 1 is pure component, right? Okay. So well, very close to pure component is infinite dilution instead. So we use infinite dilution based on the Gibbs-Duhem equation. We integrate it, and what we obtain, we found that the area under two curve A1 and A2. This is the area under curve, and this is also the area of under the curve. The area of these two curves must be equal, okay, but opposite side, in order to make it 0. Okay. So we can set the criteria for A1 and A2. Yes, both area must be equal. Okay. And this test, we call it area test. Okay, where, well, from this one you plot the graph and then you find the area. Okay. And the other technique to test the data is we call it Reddick-Kister test. And this test is based on general expression of Gibbs-Duhem equation for binary system again. This is the Gibbs-Duhem equation in terms of, in general term, okay? And we consider x0 to x1 log gamma 1 over gamma 2 dx1, okay? And here you see from Reddick-Kister test, you plot log gamma 1, gamma 2, yeah? And this is the data we obtain, right? From experiment. You draw while you find the area here and this area here. Okay. We plot well, log gamma 1 over gamma 2 like this against x1. Okay. In a semi-logarithm graph, because this one is log, this x-axis is not log. It's, yeah, x Area above, we call it A plus, and the area below, we call it A minus, okay? And the area here and area here must be equal. Okay, this is if your data pass this one, we call it passed the Redick-Kistler test, okay? And the next one is, oh, yeah, this is area test, sorry. Also, we have area consistency test. We plot the graph of log gamma 1 over gamma 2 versus x1. Okay. And there is a curve that can be linear or polynomial like this. Yeah. We draw a line on the 0 axis. And two area can be calculated above and below the axis like this. Okay. Above and below A plus and A minus. Okay. And then the ratio of the smallest and largest area, A over B, will indicate a percentage to check, okay, if the experimental data are consistent or not. Okay. So, well, you can actually there are so many tests. I skipped some, but later you can welcome back to this slide again. Okay, starting from Gibbs-Duhem equation, and then here I give you point-to-point test. The first one is point-to-point test. Okay, where this one we start from this, and how you do it. You well plot the variation of activity coefficient with composition and draw a tangent line. Okay. Then each point, you see, sorry that I don't have example here. Yeah, maybe next class I will show you some example. But here you see that you have gamma, log gamma. You have x1. And once you plot the log gamma with x1, you can find the slope, right? Slope at each point. At each point you take the slope times it with x1. Okay. At that corresponding point, you take the slope of log gamma 2 and x2 at that point. And these two terms, summation of these two terms must be 0. What does it mean? So we need some data to visualize it. Just one moment. Let me check if I have some data. Yeah, like this. Okay, we can use data to visualize. Yeah, we can plot the data like this. Okay, you have a lot of experimental data. Okay, you take the slope here, for example. You calculate the slope of gamma 1 and also slope of gamma 2. You see that the sign of the slope here and slope here must be different, right? Positive and negative. Yes. So if you can find the slope, you obtain this value and this value, right? And this one you time it with x1. Okay, and this one you time it with x2. You take summation, must be 0. Okay, so if every point satisfy this condition, it's past the point-to-point test. What is the difficult part? for using this point-to-point test. The most difficult task is you don't know the slope because the experimental data is a discrete. You have a point. You don't know exactly the slope at that point, right? So you have to estimate the curve first and then approximate the slope at that point. And of course, it contains some error because you try to, from the discrete data, you try to construct a continuous data, which is impossible in reality. Yes, but we call point-to-point test. If it passed, then it passed the point-to-point test. But anyway, you learn the basic. This is very beginning of it, right? Any question? Yeah, please pay attention to this because we have homework and some assignment, right? We have, well, we have some points for workshop. No, not workshop. Maybe it's an assignment and homework, right? Yes. And I give you data from paper, and you have to follow the thermodynamic consistency testing and construct activity coefficient model by yourself from that data. Okay. The same equilibrium must be used, must be the same equilibrium. You cannot take two equilibrium. You cannot mix two equilibrium. Mm-hmm. ใช่ Mhm. อืม หน้าแปดนั่นในหน้าแปดนั่นเนี่ยอ๋ออืมอืมเดี๋ยวแป๊บนึงนะ No. You cannot use this graph because this graph is log gamma 1 over gamma 2. You must use log gamma 1, log gamma 2. This graph, just one moment. You must use this graph. Okay? The same composition. At the same composition. Why? Because the same composition, this point and this point must be in the same equilibrium. Because it contains equal composition. Or even this one, right? The same composition, the same equilibrium. It's the same equilibrium. Okay? The difficult part is you don't have this line. You don't have this line. You have only point. point, 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 point. Yes, point, point, point. So the question is, how can we estimate the derivative? That is the challenging part in point-to-point test. No, you can approximate the curve first by any means. It's all right. You can draw it by hand or whatever and estimate possible uh, derivative. ได้ก็ทำไปได้ก็ต้องเลือกโมเดลให้ถูกใน Excel ก็ต้องเลือกใส่โมเดลให้ถูกซึ่งโมเดลนั้นอาจจะไม่ใช่โมเดลที่เราใช้ในการทำ activity coefficient ถูกไหมเพราะว่าเราไม่ใช่ใส่โมเดลอะไรก็ได้ในการทำ activity coefficient เดี๋ยวมันไม่ผ่าน give to Heming okay so it's all right so well it's okay just the point to point test is just only the what's it the development because we know it's not practical at all because we don't know the derivative so no one uses it okay so that is point to point test and the next one is area test so the idea is totally different we don't use the derivative anymore we integrate it first and identify the area instead of finding the slope we integrate it and then we find the area under the curve but again you have only point discrete point but this time you estimate the area again you have to make a continuous assumption yeah a continuous function right and then calculate that curve okay so you find that log gamma dx1 so what is the integrate of from 0 to 1 of log gamma dx1 this one you plot between log gamma right log gamma and x1 so it must be what is the area which area is it this is log gamma and x1 yes okay because you work with log gamma and dx1 And also log gamma and dx too. Okay. And find that, well, x, the area under the curve, right? From 0 to 1 and 1 to 0. Okay. So actually, it's not 0 to 1. It's somewhere close to 0 and somewhere close to 1, right? Because 0 and 1 are pure component. And also this side, well, it's 1 to 0. Okay. What does it mean? It means the whole area. The whole area here and the whole area here, right? Okay. แล้วอินทิเกรตขวาไปซ้ายปุ๊บมันก็จะเป็นลบแทนokay. This area. Okay. And also this area. They must be equal. And we call it area test. Okay. And the next one is Reddish-Kister. For Reddish-Kister, you plot log gamma 1 over gamma 2 with x1. Okay. And we estimate the area, positive area and negative area. Okay. And this positive area and negative area must be equal. Okay. This is Reddish-Kister. And the next one is area consistency test, which is we plot between log gamma 1, gamma 2 versus x1 also. Hmm. เหมือนReddish-Kister พอๆกันนะแล้วอันนี้ไม่รู้คำค่าแกมมามันก็รู้ค่าแกมมาอยู่แล้วเหมือนกันแต่ใช่อันนี้มันหารกันก่อนแล้วเดาว่าแล้วคาดว่ามันหารกันเนี่ยเอเรอร์มันจะชดเชยกัน เพราะมันเป็นอีควิลิเบียมเดียวกันโอเค there are so many test method okay to test the thermodynamic consistency okay so well other method you have to read by yourself okay of course I will find the review paper regarding the well the method to test the thermodynamic consistency. I will share with you later. Okay, so any questions for today? Any question, people on Zoom? No? Okay. So, well, I recommend you to read about the Gibbs-Duhem equation and also excess property. And then, well, make yourself more comfortable with activity coefficient model construction, how we construct it, okay? And also thermodynamic consistency testing, okay? You will use it. Okay, and then wow, we will see from the vote if well we have class on Monday or no Tuesday or not. Monday or Tuesday so it's possible. Yeah. Okay. ได้ขอบคุณครับ มาตินได้โอเคได้เดี๋ยวตอนกลางวันสมมุติได้วันจันทร์ก็ตอนกลางวันเข้าไปหาห้องครับโอเคแล้วนอนห้องแถวนี้ไม่มีละอีฟนิ่งเขาไม่เปิดให้ก็ต้องที่ภาคแหละครับ Okay, so we finish today.